Hello, everyone. I'm Christopher Januzzi, Executive Director and CEO of the Electrochemical Society, speaking to you from ECS headquarters in beautiful Pennington, New Jersey. It is my great privilege to welcome you to Day 2 of PRiME 2020 and our very special plenary session featuring Professor Nam-Gyu Park of Sungkyunkwan University in South Korea. Before we begin our formal program, I would like to first make a few brief announcements. For those of you who missed the PRiME opening ceremony yesterday, I hope you take a moment to enjoy the replay of the event available on the PRiME website. Next, we will have a question and answer period at the end of Dr. Park's talk, so please use the QA feature to share those with us. I'd also like to take a moment to thank the many wonderful organizations without whose generous support PRiME 2020 would simply not be possible. And please join me in showing our deepest appreciation to our general meeting sponsors, beginning with our platinum sponsor, SK Innovation, our gold meeting sponsor, Samsung SDI, silver meeting sponsors, Ion Power Inc., LG Chem, and Scribner, our bronze meeting sponsor, the National Tsinghua University Department of Material Science Engineering in Taiwan, and our contributing meeting sponsor, MDPI. Thank you to all our sponsors. We are very fortunate to have Dr. Kai Zhu joining us this evening to serve as moderator for Professor Park's talk. Dr. Zhu is a senior scientist in the Chemistry and Nanoscience Center at the National Renewable Energy Laboratory, or NREL. He received his PhD in physics from Syracuse University in 2003, where he studied the electrical and optical properties and the device physics of solar cells based on amorphous silicon thin films and dye-sensitized mesoporous titanium dioxide films. And since 2007, he has worked as a staff scientist at NREL, and his current interests include both basic and applied research on perovskite solar cells, including perovskite material development, device fabrication and characterization, and the basic understanding of charge carrier dynamics in these cells. So we are very pleased to have him join us today. And so without further ado, I would like to ask Dr. Kai Zhu to take the virtual podium at this time. Take it away, Kai.
Thanks, Chris. It's my great pleasure and honor to introduce our plenary speaker, Dr. Nam-Gyu Park. Dr. Park is a professor and SKKU fellow at Sungkyunkwan University School of Chemical Engineering. His research focuses on high efficiency, mesoscopic, nanostructured solar cells. Actually, I have known Professor Park for a very long time. About 20 years ago, when Professor Park was a postdoc at NREL, working on dye-sensitized solar cell. I was a graduate student doing some characterization on the dye cell that is made by Professor Park. So now we all know that Professor Park is a pioneer on the solid state perovskite solar cells. In 2012, Professor Park reported the first stable and efficient, about 10% efficiency, solid state perovskite solar cells, which lead to an explosion in the perovskite research. In 2017, Professor Park was named a citation laureate scientist worthy of a Nobel Prize. So today, Professor Park will review the past research and the future importance of perovskite, unique optoelectronic properties which make it a viable, efficient, and cost-effective alternative, not only for photovoltaics, but also for X-ray imaging, light emitting diodes, lasers, hydrogen production, and even lithium batteries. So please join me in welcoming Professor Nam-Gyu Park.
Good morning, everyone from South Korea. Thank you, Kai, and thanks all the committee members for inviting me to the plenary lecture session of the PRiME 2020. I'm again Nam-Gyu Park from the Sungkyunkwan University. I'd like to give a talk about the perovskite solar cell past 10 years and the next 10 years. Okay, so the first I'd like to give a brief introduction of the history of perovskite solar cell, how we discovered the solid-state perovskite solar cell. Actually, I have been working on solar cells since 1997 at National Renewable Energy Lab. At that time, my supervisor was Dr. Arthur Frank. He is very kind and very gentle man, but he was now retired. At that time, I studied the dye-sensitized solar cell having liquid electrolyte and mesoporous titanium oxide. At that time, I made the efficiency 9.2% dye-sensitized solar cell, which was second world best efficiency. However, the efficiency of dye-sensitized solar cell is limited to 12%, around 12%, since 1997. At that time, the efficiency started with the 7%. However, a few years later, the efficiency goes up 10%. However, the efficiency is almost saturated up to now. The limitation of the efficiency of dye-sensitized solar cells is probably due to low absorption coefficient of the organometallic sensitized, ranging 10 to the 3, the inverse centimeter. Therefore, people would like to replace the organic sensitized to increase the further efficiency. The inorganic quantum dot is a potential candidate because it has very high the absorption coefficient. For instance, if you use the lead sulfide, which is the very narrow band gap of about 0.5 eV. However, if you decrease the size, then you undergo the quantum size effect, and then the band gap increases to about the 1.1 eV, which is suitable for the photovoltaic material. However, when you decrease the particle size, then you, at the same time, you increase the surface traps, which can act as the recombination center. Therefore, you cannot expect a high open circuit voltage. Even though the band gap is 1.1 eV, you have the around 0.4 or 0.5 volt. Therefore, the inorganic quantum dot was not successful to replace the organic sensitized. And then while I'm searching the candidate to replace the organic sensitized, I was invited to Nano Euro 2007. And then this is the dye-sensitized solar cell related conference. There, the very special the talk was given by Tom Miyashaka, and the topic was the perovskite-sensitized dye-sensitized solar cell. The perovskite is the crystal structure with the chemical formula of the ABX3, and A site cation has the octahedral geometry, and B site cation has cube-octahedral geometry. And then at that time, the Tom Miyashaka reported the efficiency of around the 2 to 3% using the perovskite sensitized deposit on titanium oxide here. However, when I take a look at his the IPC spectrum, then the spectral feature looks like very ideal the shape. However, the absolute value was a little bit lower than the 50%. So there is a lot room to improve the IPCE. Right, coming back after 2007, the Nano Euro conference, I studied the perovskite solar cell, and then the 2011 we reported the perovskite sensitized solar cell showing the efficiency 6.5%, and then we actually provided a very the excellent recipe to form the stable the methyl ammonium lead iodide by varying the concentration, by optimizing concentration of the precursor solution. And shown here is the, at that time, the quantum dot morphology, the perovskite is sitting on titanium oxide. And then the even film thickness is much lower than the Tom Miyasaka's the film thickness of about 8 micrometer. However, the big issue in the perovskite is which is well dissolved in polar liquid electrolyte. Shown here is the once you inject electrolyte into the perovskite-sensitized titanium oxide, in few minutes the perovskite dissolved completely. So I like to replace the liquid electrolyte with some solid hole conducting material. And then the first attempt was tried with P3HT. And then the first trial was not successful because the large polymer material is difficult to infiltrate it into mesoporous titanium oxide. So I like to switch the polymering material to molecular hole transporting material such as the spiral compound here. Shown here is the spiral backbone. However, we tried the spiral compound and a little bit increase in the power conversion efficiency. However, when we change the film thickness from 1.2 micrometer to 1.8 micrometer, the efficiency is, would not go up. Therefore, we would like to find out some useful method to improve the efficiency. And then immediately we recognize that the perovskite has the 1 order of magnitude higher the absorption coefficient as compared to the N719 die. So based on the very simple the Beer-Lambert law, the film thickness is inversely proportional to absorption coefficient. For instance, if you have the 1 order higher the absorption coefficient, you don't have to increase the film thickness. Therefore, we decrease the film thickness from 2 micrometer to 1 micrometer, and then immediately we found that the efficiency is gradually increases from 5.6% to 7.3% efficiency. We would like to further decrease the film thickness up to 0.6 micrometer, and then the efficiency gradually increases, which is because of the increase in open circuit voltage and increase in fill factor without sacrificing the short circuit photocurrent density. So eventually we got 9.7% efficiency and showing the 500-hour long-term stability even without encapsulation of the solid-state perovskite solar cell. And then we first report the stable high-efficiency solid-state perovskite solar cell in 2012. And then now this paper cited the approaching 6,000 times as of today. If you take a look at the some research activity seen from the publication, the 2009, the one paper came out by Professor Miyasaka, and next year we don't have any the follows. And then 2 years later, we published the second paper, but still including the liquid electrolyte, which is not stable. However, after publishing the stable solid-state perovskite solar cell in 2012, then the publication increases, looks like the exponential increase. And then last year we have about the 4,000 publications. And in terms of the average annual growth rate of the power conversion efficiency, perovskite is determined to be about more than 10%, which is which is indicative of a very rapid increase in the power conversion efficiency rate. as compared to the conventional inorganic solid state, inorganic the semiconductor solar cells. Now the perovskite solar cell reaches the 25.5% efficiency, which was recently reported some best efficient charter in NREL the webpage. In our lab, after achieving 9.7% perovskite solar cell of the solid state version, we have focused on the pure the perovskite having the methyl ammonium in A site or the foam ammonium in A site, because we would like to focus on the pure the phase pure composition instead of the mixed composition. The mixed composition may undergo the phase transition, which may not be suitable for commercialization. And also, the FA-PBIC is the best option because the band gap is more appropriate to the shock request limit. Now, I'd like to give talk a little bit about the progress of the perovskite solar cell in terms of the efficiency improvement. The band gap structure can be easily established from the molecular orbital theory. And then when you establish using the molecular orbital theory, using the PV atomic orbital and iodide atomic orbital, and then you will find that the valence band is composed of the anti-bonding property. So the anti-bonding property gives you a defect tolerant the characteristics, which is a unique property of a perovskite as compared to the conventional inorganic semiconductor. And also the perovskite has pretty much high absorption coefficient, even better than the gallium arsenide, because of the P to P transition. And then this is more efficient because of less dispersed with p orbital as compared to s orbital. And also, for instance, usually dielectric band gap transition material has a very strong absorption, but a very short Kera lifetime because of a dielectric band gap transition, the energetics. However, the perovskite has very strong absorption along with long carrier lifetime. This is because the spin-orbit coupling the characteristics. The carrier transport property recently measured by the photo Hall effect measurement, and then it was found that the MA-PBIC or the FA mixed phase, the polycrystalline film shows the micrometer scale diffusion length. And interestingly, electron and hole transport is almost balanced. And therefore, it is very good to the design the perovskite solar cell structure. So the device design rule is here. We have 4 different kinds of the devices for perovskite solar cell. One is mesoscopic and serve the perovskite structure. This is the first version. And next version was the mesoscopic field perovskite solar cell. And then recently, people frequently use the normal planar structure or inverted planar structure. However, in that case, you have to consider the electron hole diffusion length and mobility. If this is the unbalanced, then probably the mesoscopic field structure is better. For the case of balanced electron hole diffusion length, then the planar structure is pretty much suitable. And past the 10 years, the efficiency was significantly improved from 9.7% to 25.5%, which is pretty much close to crystalline silicon solar cell. They're almost comparable. And this efficiency improvement was realized by the coating engineering and compositional engineering. For the coating method, now people use the frequently the adduct intermediate method, which comes from the Lewis acid base, the adduct. And for instance, if you the deposited precursor solution, drop precursor solution on the spinning the substrate, you have to include the DMSO, and then during the spinning, while spinning, you drop the diethyl ester, which acts as the anti-solvent, and then immediately you can get the transparent film, which is due to the adduct intermediate. And then after annealing, you can get the high quality MAPBI3. So adductor is kind of the can control the crystal growth of the perovskite film. Regarding composition, we start with the MAPBI3. However, as I mentioned that the FAPBI3 is better than the MAPBI3 in terms of the light absorbing property because of narrow band gap energy, and therefore the absorption can extend to 840 nanometer as compared to 780 nanometer for MAPBI3. However, the FAPBI3 is quite unstable at the room temperature. The alpha phase transforms to the delta phase at the room temperature. Therefore, it is necessary to stabilize alpha phase FAPBI3. In that case, if you use the cesium or methyl ammonium cation, then you can stabilize easily alpha phase FAPBI3 even at room temperature. So cesium, methyl ammonium, rubidium, the smaller cation for FAPBI3 is called the stabilizer. The one unique the property of the perovskite solar cell is the hysteresis. So hysteresis comes from the capacitive current at the electrode, and which is quite dependent on the composition here. Recently, there is a lot of method to solve the hysteric behavior. And in addition, if you have the very severe hysteresis, then you cannot guarantee the stability of perovskite solar cell, because the hysteresis is quite related to, is closely related to the defect. So if you create a defect, then you cannot guarantee the stability, because defect is the kind of the seed for the propagating the instability. We recently found that the perovskite undergoes a Frankel defect. To protect the Frankel defect, if you include a small size the alkali metal ion such as potassium ion into the interstellar site, then you can effectively protect the Frankel defect. Therefore, you cannot see any pronounced hysteresis here. So we actually, this is a visual, for instance, this is control devices, and this is potassium doped devices. Then there is, this is a PL image, and the in situ PL image, you can see that there is some, the disappearance of the PL image at the electrode interface. This is due to the ion migration. However, after you, the doping with potassium, then you can hardly see the ion migration. Let me move on the perspective of the perovskite solar cell. For next 10 years, we probably get the higher efficiency, and we have to focus on stability. And then the upscaling is a very critical issue for commercialization. And higher efficiency to the Shockley case emitter, the limiter, and better stability, and upscaling issue, and also material issue for commercialization. And to solve that kind of the issues, first we have to think about the lesson from the past 10 years. For instance, this is a certified efficiency going from the 16.2% to 25.2% last year we achieved. And actually, there is no significant increase in short circuit photocurrent density. However, a lot increase in the open circuit voltage, and then from 23.3% to going up to 25.2%, 25.2%, the additional increase was achieved. For instance, the large increase in the fill factor. So, for instance, a 25.2% efficiency cell has the 1.18 volt and 25 milliamps per square centimeter, and the fill factor is crossing the 0.85. However, in terms of the shock frequency limit, still we need improvement of the short circuit photocurrent density and a significant increase in open circuit voltage and fill factor as compared to silicon and gallium arsenide solar cell. In order to increase the open circuit voltage and fill factor, usually we have to control the recombination. There are 3 different recombinations here, and then the SLH recombination is critical in determining the open circuit voltage. In addition, the interfacial recombination is very critical in determining the open circuit voltage. For instance, if you manage the interfacial engineering, then you can increase the open circuit voltage and fill factor. However, there is no significant change in short circuit photocurrent density. And then after that, if you treat well the bulk engineering, bulk property, and then you can remove the SLH recombination, and therefore at that time, for this case, then you can increase the short circuit photocurrent density, open circuit voltage, and fill factor. Therefore, if you allow only the radiative recombination by removing SLH recombination and interface engineering, interface recombination, then you can expect a 30.5% efficiency with a 1.3 volt and 0.9 fill factor. So if you, for instance, the perovskite itself can show the high open circuit voltage. However, if you add some interfaces, if you increase the interfaces, then you can gradually, you expect a gradual decrease in open circuit voltage. So interface is very important. There are so many interfaces in both normal structure and inverted structure that you have to consider every kind of interfaces, including the grain boundary of the perovskite. For instance, we inserted the interfacial layer in between the tin oxide, ETL, and the perovskite, and then we found that the increase in open circuit voltage and a slight increase in fill factor without a change in without a significant change in short circuit photocurrent density. So this is a proof of concept of this the theory. For instance, grain boundary engineering, we add some additional the excess materials in precursor solution. Then this additional excess precursor material can sit on the grain boundary. That passivate the grain boundary. Therefore, you can increase the open circuit voltage and fill factor. There is no significant change in short circuit photocurrent density at a given composition. And also after you deposit and anneal the perovskite film, then the surface is exposed to the air or environment. Therefore, there is some the degradation on the surface of the perovskite. Therefore, you need some interface engineering on perovskite surface. And then the interlayer can passivate between the perovskite and ETL. And by doing this, you can increase the open circuit voltage significantly, and at the same time, you can decrease the trap density. Therefore, you have the increased open circuit voltage and fill factor. When you select the interfacial engineering material, you have to consider the functional group. We tested electron donating functional group and electron withering functional group. and eventually found that electron donating functional group working very well, improved the performance. However, the electron withdrawing group is the other way around. This is because there is some defect comes from iodide vacancy or the lead 2+ vacancy. Then this electron donating, because the electron donating functional group improved the performance, that indicates that there is iodide vacancy in pristine perovskite material. So for bulk engineering, usually probably the flat surface may be better to contact the whole transporting layer. However, we found that from the optical simulation, the wrinkle structure is better than flat surface. Usually, the flat surface comes from some kind of the tension on the surface of the perovskite film. If you have the some compressive strain, then you can have the wrinkle structure. So we can control the various kind of the wrinkle morphology by tuning the amplitude and the wavelengths of this wrinkle structure. And then interestingly, we found from the fluorescence-lifetime imaging microscope combined with the time-correlated single photon counting, then the A and the F indicates the heel of the wrinkle structure, and B and G stands for belly, the state of belly of this wrinkle morphology. And then heel state has a higher, the longer carrier lifetime than belly state, which is very good, which means that this heel state has a highly crystalline structure. However, the belly state is a less crystalline state. So this is good for electron transport for the wrinkle morphology perovskite solar cell. And then we also tested the long-term stability, which is a light soaking test over 10,000 hours, 1,000 hours, and then we found that after 1,000 hours, the initial efficiency of about 84% efficiency of the initial efficiency was remained. And also in terms of the moisture stability, we recently developed the paradoxical approach with a hydrophilic passivation layer. Usually people would like to use the hydrophobic passivation layer to protect moisture from the environment. However, in that case, if you use the hydrophilic passivation layer, you need a long chain alkyl, the long alkyl chain compound. In that case, you probably increase the resistance between the perovskite and whole transporting layer. So instead of that, we use a very short the alkyl chain. However, with the hydrophilic property. And interestingly, we found that the hydrophilic passivation layer protected well the perovskite layer from the environmental moisture. And the normalized PC shows that the long-term stability is pretty much better than without passivation. And also, in terms of the thermal stability, for instance, the spiral compound having the additive like the LiTFSI is not good for the thermal stability, which is because the lithium cation easily migrate to the perovskite layer, and then in that case the HTL, the whole conductivity will be lost or will be lowered. Therefore, the efficiency is significantly decreases with the time. So we recently developed the very good whole transporting layer which can capture mobile lithium ion. And then therefore, we prove that the very nice thermal stability at 85 degrees C over 1,000 hours. And then for upscaling, probably we cannot use the conventional coating solution frequently used for spin coating. Instead of that, we recently developed a very good precursor solution without having DMSO, the polar protic solvent, which cannot be evaporated during the debar coating here. Instead of that, we actually can make the very nice perovskite film in very large area without the polar protic solvent. So we actually prepared the very the excellent perovskite precursor solution using acetonitrile, which is easily evaporated during the debar coating. However, we can get the very nice crystal structure and morphology. And for upscaling, the material may be issue. And recently, the people are using the high quality, very expensive PBI to get the high efficiency perovskite solar cell. However, which is not the suitable for commercialization. So you would like to use the very low grade PBI tool. Using this low grade PBI tool, we made high quality the perovskite powder. For instance, this is at the room temperature. You can make the perovskite material FA-PBI3 or MA-PBI3. The FA-PBI3 is not perovskite structure. This is a delta phase non-perovskite structure, which can be prepared even at the room temperature. And using this FA-PBI3, we can get very highly crystalline the perovskite structure without the trace of the PBI2, and the defect is pretty much removed, and carrier lifetime is pretty much increased as compared to the precursor mixture method, and also the ideality factor is close to ideal device structure formed by the powder method. And then there is still a little bit the hysteresis. However, we made the 130 cells, and then the efficiency, the statistical data shows that very reproducible power conversion efficiency. And with this powdered perovskite material, we certified the 21% efficiency, which is consistent with the data we measured in our lab. Now let's wrap up my talk. In 2012 we started 9.7% efficiency on the solid state perovskite solar cell, and then during past 10 years, the people's devoted a lot to increase the efficiency by compositional engineering, and eventually the PC is of about 25.5% was recently achieved. And to go up further, the 30%, the reaching the shock recoil limit, then the interfacial engineering is very, very important, and also the bulk engineering at the same time to remove the some defect for recombination. Therefore, interface engineering becomes more and more important to reach the theoretical efficiency of around 31%. And then interfacial engineering also guarantee is improve the stability also. And for upscaling, then the materials and coating method needs to be newly developed. And I like to emphasize that the synthesized very inexpensive perovskite powder is very good for the reliable and reproducible large area perovskite solar cell. I think in my opinion, tandem, meaning that top cell with the perovskite solar cell, the bottom is silicon or the CIGS solar cell, this kind of tandem may be a highly marketable technology as a first strategy. So I'd like to thank the student. They got already a doctoral degree and then now working on the university and company. And finally, I'd like to thank the student in my lab. Thank you for listening. Thank you very much.
Well, thank you, Dr. Park, for that wonderful presentation. We're now going to move into the question and answer phase of our talk tonight. And I'm going to turn it back over to Kai-Zhu to help lead us through that.
Thanks, Chris. Thank you very much, Professor Park. The talk was very nice. So I will start with some questions. So probably later our audience can send in submit some questions. So I will. So first, actually, I'm very glad that you mentioned about a tandem, right, close to your last slide. I'm really also a big fan of tandem. So I noticed that for the tandem research, for example, in the United States, right, there are many groups working on tandems, right, including perovskite silicon, perovskite CIGS, perovskite, right? But it seems to be a little bit less enthusiastic in Korea, right, working on tandem, right? So do you know why that's the reason, or do you have any comment about the single junction versus tandem? More comment?
Okay. So I like definitely say that Korea, the companies are working on tandem. For instance, we have big company Hanwha and LG. They probably are working on the tandem structure. You see, in university, it is very difficult to access to the bottom cell, the silicon or CIGS, because if we have some very good communication between us, for instance, the silicon people and the perovskite people, then maybe it happens. But we do not have that kind of the circumstances, environment, that kind of mood. So now the silicon peoples and the CIGS peoples are interested in the tandem structure. So this is not easily accessible.
Okay, so
companies working on the tandem structure.
Okay, so it's more a resource issue, right, for the university groups. Because
right.
They have access to that.
Yeah. Right.
Okay, so but overall, I think the working on tandem is should be it represents a promising direction, right? So
yes, I think so.
Right, can work on it.
I think so. Yeah.
So that probably can transition into the marketplace sooner than the single junction applications. Okay. I have another question. You talked about for the next 10 years, right? So one of the focus is really on the scaling, upscaling. So which is very, very important. When it comes to the upscaling for the module production, module development, we are often facing many questions. So people have probably already asked you. So here I will ask the question that some people ask us at NREL, right? So what device architecture should I use, right? What perovskite composition should I use? And which coating technique should I use, right? So because once you, especially for a company to work on perovskite solar cell product, right? If that's their aim, right? They have to decide from early on, right? Otherwise, they're wasting a lot of investment. So what is your recommendation or comment for the, well, very interested in pushing this into the commercialization stage?
Yes, so for the large upscaling, the structural point of view, device structural point of view, I think the normal, the planar structure may be the easy way to go instead of the mesopore structure, because mesopore structure is difficult to infiltrate the precursor material, and also the depending on viscosity of precursor solution. Therefore, the planar structure may be better. Usually, normal planar structure is better, including spiral compound, if we guarantee the long-term stability. However, we experienced that the spiral is very difficult to for the guarantee the thermal stability. Therefore, we need some new materials. As I presented, if we develop the comparable, the whole conducting material, organic whole conducting material, with very good thermal stability, then I think there is no problem in normal planar structure with the whole conducting materials, because this is very easy way to get. And if we cannot succeed the normal planar structure for upscaling, then probably we have to switch on the inverted structure. We found that inverted structure is better in terms of the thermal stability. I'm thinking of thermal stability is most critical, the stability issue, as compared to the some moisture stability and light soaking stability, because moisture stability can be protected by encapsulation. But the thermal stability is related to the material issue. So the inverted structure, without using the spiral hole conducting material, for instance, some inorganic or the organic hole transporting layer and the PCBM of carbon-60, the inverted structure is much better in terms of the thermal stability. However, those inverted structure is inferior is lower the efficiency than the normal structure. So there is some pros and cons. But I think the only single junction perovskite solar cell, the normal structure, maybe normal planar structure is a better choice. Coating technology, I think the slow die coating is very good method, but we found that the slow die coating is very slow die coating is very good. If we develop, it depends also, it depends on the precursor solution. So the coating method and also upscaling, for upscaling, the very useful, very good, excellent, the precursor solution. Developing a precursor solution is very critical, very important for upscaling. So far, people are working very hard, but I think the debug coating or the slow die coating is so far the best way to increase the size. Well, spray is very difficult. You know, the spray is very good method, but there are the solution, maybe a lot of solution should be consumed for spray coating. So debug coating or slow die coating will be one of choices for upscaling.
Okay. Yeah, very nice. Thank you. And so audience asked one question about the lead. What is your view about the environmental impact from lead? I want to expand on that, not just lead, right? So now there's some discussion about the solvent impact, right? For example, if you use DMF, NMP, or some other standard polar solvent, right? When you do the perovskite fabrication at a large quantity, those are not very friendly to human health, right? So the toxicity, the environmental impact, what is your comment view?
Yeah. Actually, if you are a scientist, then the PbI2 is pretty much insoluble in water because of the very low solubility product. This is the data. Okay. So I think if there is some decomposition of the perovskite to produce the PbI2, PbI2 is quite insoluble. Therefore, probably we don't have to concern about that much about the lead release. However, we have to anyway concern about the lead toxicity. In any case, uh, uh, we probably learn from the cadmium telluride technology that in which the cadmium telluride adapt the recycling the method. So the recently our friend they published a paper about the recycling method, which was published in Nature Sustainability, and so he mentioned that the perovskite solar cell is fully recyclable. So we have to develop the very useful recycled method. Then probably we can protect release of the PV to environment. And also I'm thinking of some kind of the invisible PV. That means if we have some break the perovskite solar cell and release the perovskite into environment, we don't see any kind of we cannot the PB2 plus if the PB2 plus cannot be detected, then it's very good. So chemically we can treat the lead. It's not to be released to the environment. Okay. And then, so therefore, we also discuss about the lead toxicity, lead concern, but we have to anyway concern about the lead, and then recycling method may remove the concern about the lead toxicity. Solvent is very important issue. In industrial, for instance, DMF is not used for solvent. And also, most of the polar protic solvent is not good for the industrial application. So only DMSO is proved to be green solvent. But unfortunately, DMSO, if you use only DMSO, it's very difficult to make the high quality the perovskite the film. However, recently people published if you add a certain the proper additive into DMSO based precursor solution, then you can improve the film quality. So now we have to think about also the green solvent issue, as well as the lead toxicity. That's my answer.
Okay, yeah, that's very, very, very helpful, very useful. There are a few more questions from the audience. One, clearly the powder, what you showed for the powder, right, approach, for the FEPPS3 powder approach is very interesting, very exciting, right? I think that's very, very valuable and for the future large scale fabrication, right? So that's for FEPPS3. So one question is, if we want to use this powder approach to make other composition, more maybe a little bit more complicated compositions, how easy is this approach? Can we use this approach to generate, let's say, cesium FAMA mixture with iodine bromide, right? So is that easy to do, or is it easier to just work on very simple stoichiometry?
The initial idea, the first idea to synthesize the precursor powder, perovskite powder, actually is not aiming at the large scale, because we found that there are many reports regarding non-stoichiometry of the perovskite, which can cause some defect or some the side effect, negative effect. So we would like to start with the stoichiometric perovskite powder, which can produce the stoichiometric composition. So this is our first idea. And then for this precursor powder, we don't have to use the high quality PBI2. Now we use the 95% low grade PBI2 is okay. And then we confirm that the almost 100% pure the FA-PBI3. For the mixed phase, you can include a certain amount of cesium then you can collect the as powder form. Even, for instance, Fa cesium lead iodide, for instance, you can collect the Fa cesium lead iodide powder form. Then you can use this powder to make the perovskite film.
Okay, yeah, thank you. There are a few other questions related to efficiency from the audience. Okay, so for the single junction small area device, let's say 0.1 centimeter squared, right, the standard lab scale, efficiency are already at 25.5.
Yeah.
First question is, how high can this go? What do you expect this, where do you expect this can reach? So that's one for the small area device. Another is, we also need to spend a lot of effort working on the large scale, right, module. Right now, the module efficiency is clearly below 20%, maybe 18, 19% from the PV efficiency table. So there's a big gap. How do you, what's your comment or what's your view about reducing that gap?
First, the last question about the last question. Second question, the perovskite, the history is about less than 10 years. If you start with the solid state perovskite solar cell, then we just spent 8 years, and the society achieved it. So almost 26% efficiency. This is a very great job, I think. And also, even large scale, very short period. The large scale, I think the 1 or 2 years is the 17%, 80% is very close to the theoretical efficiency. The large scale, I think if we apply the company is getting involved, the large scale, then quickly improve the efficiency. This is technical issue. I think some scribing and some very homogeneous large area coating, something like that. So the data space, if you decrease the data space, then you can increase the efficiency, I think. And the first question, excuse me, first question is,
where can we go for the single junction device efficiency? Now it's 25.5. How high?
Yeah. Yeah. So I think well, this is a kind of the secret. Recently I have thought that based upon gallium arsenide, they achieved almost the theoretical open circuit voltage and fill factor. Yeah. So the perovskite also can get that kind of the theoretical value. The open circuit voltage 1.3 volt and the 0.9 fill factor. So people are focusing on interface engineering, but at the same time we have to focus on the bulk engineering. So bulk engineering means that still we have the some imperfect perovskite crystal. Probably the Ma and Fa or the cesium may not be the best the A-side cation. So I think that we discover a very new A-side cation. So this is a very interesting journey. I'm seeking the A-side cation to get the 30% efficiency. Even though we cannot get the 25% efficiency, the Professor Sang-il Seok can get this high efficiency. But actually, I'm thinking of that kind of the bulk engineering, which is very important.
Okay, yeah, that's very nice insight. There's another question about the how when you study, when you learn a lot of lessons on one perovskite composition, how easy can you translate that to another composition? Actually, I know the answer is very difficult, right? So I will rephrase the question in a different way. People like to have, we want to have both high efficiency and high stability in one package. Right now, the effort is getting into a more simpler composition like FEPBS3, which has very high efficiency at this moment, right, about 25%, but the stability is relatively poor. But on the other hand, when you add those small acid ions, the cesium, Ma, Fa, or bromide iodide, then you get a relatively more stable material, perovskite. But it seems that the efficiency has reached it kind of bottleneck, right? So how to balance and what is strategy to maybe merge these two approaches together?
So Kai, that's very good question actually. This is for next 10-year strategy, research strategy. So I'm thinking of that, for instance, FA PBIC is quite unstable because of the A site cation. MA PBIC is quite stable, relatively stable than FA PBI3. So because of the instability of FA, the cation in A site, so people would like use some of the other elements such as cesium or the MA. And also, if we increase the efficiency, then we may not guarantee the stability using only the FA PBI3. That means if you take a look at the crystal structure in terms of the packing model, then the perovskite has the ABC cross packing model that leads to the cubic cross packing. And then the one plane, if you take a look one plane, then the one plane has the 75% the iodide and the 25% A site cation. So there is some the mismatching between A site cation and the iodide anion. So A site cation now is very, very important to stabilize the crystal structure. So we have to find another, probably not discovered, so very unique the A site cation to stabilize and to increase the theoretical to reach the theoretical efficiency.
I totally agree. That's very, very nice. Very good. Yeah.
Well, I think Professor Park, with that view into the future, we've reached a great spot to wrap up this session.
Thank you.
Oh, thank you. And actually, I would ask everybody to join me in thanking first our moderator, Kai Zhu, for leading this wonderful discussion. And of course, to our keynote speaker, Professor Nam-Gyu Park, for sharing his wealth of insight and knowledge with us today. It was really a fantastic session. So I'm so glad we could bring this to everybody at PRiME 2020. I would like to again thank our sponsor, our platinum sponsor, SK Innovation, and all of our meeting sponsors for their generous support of this session and the conference in general. And I should also remind everybody that we will be hosting live events throughout the opening week of the conference. Coming up tomorrow evening in the US, Wednesday morning in Asia, we will feature the Electrochemical Energy Summit, or E2S, on the electrification of transportation. On Wednesday evening in the US, Thursday morning in Asia, we are proud to bring you a very special event, The Legends of Battery Science, a celebration with Nobel laureates M. Stanley Whittingham and Akira Yoshino. So please be sure to join us for that. It'll be a very special event. And finally, we will end the week with the ECS Awards ceremony on Thursday evening in the US, Friday morning in Asia. So please be sure to join us for all of these wonderful live events. And really, thank you again to Professor Nam-Gyu Park and for Dr. Kai Zhu for being with us today. And with that, I wish you all good day, good night, and we will see you all week long here at PRiME 2020. Thanks again, Dr. Park, Dr. Zhu. It was a wonderful event. Be well.